When I was in college, my friends and I had a problem attracting the attention of girls, quite frankly. So we came up with some pretty interesting schemes to try to draw attention to ourselves. And this is one of them. At Cal Poly, they have these 3-story red brick dorms. And there was a dorm that basically, this is kind of a cross section of it. And so there was, this is the top floor, second floor. And then there was a hallway in here, right? And then you had the dorm rooms, and each dorm room had a window like this and this. And so we were playing this game where, I'm not sure how safe this actually was, but there was, on this side of the building, there was the intended target. There was a bunch of girls that probably very wisely were not paying any attention to us. So what we decided to do was to try to launch water balloons at the girls, but from the other side of the building. And so what we did is we got some surgical tubing, and we tied them together and made a big slingshot out of it. And we had a bunch of water balloons. By the way, this is really why you want to go to college, is for stuff like this. And so we had a guy that would stand up here and yell at us, and then to tell us, where to fire the water balloons. So there's a bunch of us over here, and we're trying to aim. So we pull this thing and we launch the water balloon, okay? And it's got a certain velocity, right? Which includes its magnitude, how fast it's going in meters per second, and a certain angle that it makes with the ground. Okay, now, so obviously what happens is that once this object, this water balloon, leaves the slingshot, it is now on a path, which always missed, no matter how hard we tried. And see a little splat right here. But for the purposes of this class, we're going to assume that the water balloon is only under the influence of gravity as it travels. There is a little bit of wind resistance, and if you go on in your studies of physics and engineering, aeronautical engineering or mechanical engineering, you will study the effects of wind resistance, but the equations for it are crazy hard. So we're not going to do that. We're going to assume that this is on the moon or something. There's no atmosphere. Or we're just going to assume that it's negligible. And it's pretty negligible for these slow speeds. So what would happen is that they would launch this water balloon, and the balloon would go on this path called a trajectory. Okay, and the trajectory, a trajectory is the path that an object follows through space. This shows the path that this thing will travel through time, and that's called a trajectory. Well, but the only acceleration that this water balloon experiences is the acceleration due to gravity. Okay, there's nothing. Well, there is a little wind resistance, but again, we're ignoring it. And so the only thing this water balloon has that's changing its velocity is the acceleration due to the pull of Earth's gravity. When that's true, when an object is only under the influence of gravity, so the only acceleration it has is the acceleration due to gravity, that object is called a projectile. Okay, and later on in your career, a projectile will include wind resistance. A former student of mine, a kid named Nathan Lawchuck, he's in the Army right now. He's just getting back from Afghanistan, but he runs a battery of artillery. And of course, their job is not to lob water balloons, but to lob, quite lethal objects to groups of people that are actually the only time they really use them is when those people are trying to kill them. So, I mean, it's pretty awful. But they have to launch a projectile, and as it moves, they have equations that describe where this thing will land based on how fast it comes out of the gun and what angle it's inclined at. And then, of course, they have to take into account wind resistance. We're going to keep it simple and just ignore wind resistance. And we're not going to shoot lethal shells. We're just going to shoot water balloons. Okay? Now, actually, just to tell you the sad result of this story, this person would run over and say, no, you missed. You need more angle. You need more angle. And then we would launch it, and he would run across the hall and look to see where the water balloon landed. Okay? Well, so it didn't work. So he ran across, and he said, no, less angle, less angle. So we did too little angle. And so what happened is we actually launched the water balloon right into the window. But there was a screen window, and the water burst. I mean, the water balloon burst, and it was truly amazing because when it hits the screen at that high velocity, the screen actually vaporized the water into, well, not vaporized it, but it turned into billions of little tiny water droplets, and it coated the entire room with spray water. Everything got wet in the room, which we found delightful because it wasn't our room. Okay, and by the way, there's all kinds of things that you can do in the dorms that are really quite fun and involve a little science, you know. All right.
How was this supposed to attract a positive attention?
Well, we didn't necessarily want positive attention. We just wanted any kind of attention. We figured any kind of attention was better than what we were getting. So, look, if you have the perfect speed and the perfect angle, though, you will be able to hit the target. And there's some really fun computer games where you can, try and do that. Or Angry Birds, right? You play Angry Birds. That's basically what you're doing. This wasn't really Angry Birds. This was just sad, pathetic guys. But anyway, so what we want to do is figure out how to deal with this. Now, what we have so far, let's take a look at the water balloon right here. The only acceleration on the balloon is in the downward direction. So, I'll just redraw it right here so it's a little bigger. This is the only acceleration in our problem, and that acceleration is equal to negative 9.8 meters per second squared j hat. Now, by the way, 9.8 is the magnitude of the acceleration. Negative j hat is the direction of the acceleration. So what this does is that this allows us to use the kinematic equations to solve problems. And those kinematic equations, it's basically like what we did last time, at least with assignment 1, but it's even simpler in a way because there's only one acceleration in one direction. So what we can do is develop a set of kinematic equations that we can use to solve these projectile motion problems. And that's what we're going to do right now. We have, let's take a look in the horizontal direction, the x direction. And just for the purposes of this, I'm going to say this is the x direction and this is the y direction, okay? So in the x direction, just looking at it in terms of the kinematic equations, I can say, oh, okay, well, the final velocity in the x will be equal to the initial velocity in the x plus the acceleration in the x times time. And after all, the acceleration in the x direction is a constant, and it's okay to use the kinematic equations. But what is the acceleration in the x direction? For a projectile like this, it's 0. So this just reduces to this. Vx equals v naught x. Now what does that mean? I mean, we've written an equation down, but what does it mean?
So the x direction is constant?
Yes, it means the velocity or the horizontal component of the velocity of the projectile doesn't change with time. It stays constant. So if I were to follow this projectile all through its path and just look at its the horizontal component of its velocity, even at the very top, right? It's still moving. It's still moving. It's still moving. Am I on screen? No, it went off screen. And it's still moving. Even just before it hits, here's the water balloon just before it hits. We're saying that it has the same horizontal velocity that it started with. So there's no change in the horizontal velocity. The horizontal component of the velocity is constant. Now, let's take a look at the next kinematic equation, where we say delta x equals Vx plus V naught x over 2 times t. Right, this is the average velocity. But if these are the same, if Vx and V naught x are the same, you're just adding the same thing to itself. When you add something to itself, you have 2 of that thing. So this just becomes 2 V naught x, and the 2 will cancel. And so you have delta x is equal to V naught x times t. Now this is really the only kinematic equation that you are really going to use very much in the horizontal direction for projectiles. And this is just saying, hey, the velocity is constant, just multiply that velocity times time, and you've figured out how much you've changed your horizontal position. And if you want to know how far it goes, I mean, this could be delta x. If you know the time that it took to fly, you can figure out what that horizontal change in position is. Okay, now the third kinematic equation, I'm kind of running out of room here, but delta x equals V naught x times t plus 1/2 a t squared. Well, if the acceleration in the x direction is 0, this term just goes away. So you're just left with the kinematic equation I started with. That we got using the second kinematic equation. You just have this. And then, of course, we have the fourth kinematic equation, v squared equals v naught squared plus 2a delta x. Of course, this is ax. This is vx, v naught x. Well, this acceleration right here is just 0, so this term goes away. And you get Vx squared equals V naught squared. You take the square root of both sides, and you just get what you got over here. That the velocity in the x direction is constant. Now, in the y direction, you've got a different story. You have Vy equals V naught y plus ayt. Now, what is ay? What is a in the y direction? Negative 9.8 meters per second squared. Now the book uses, a lot of people use g. If you want to use g, that's fine. I just keep it as a, because then I only have to memorize one set of equations. And then the second kinematic equation, delta y equals v naught y plus vy over 2 times time. So that didn't change at all. Okay? Look, the velocity in the y direction, if we go back to my example problem, obviously, here the y component of the initial velocity is quite high, and then gravity shrinks that until at the very top the y component of the velocity is 0 at the very top, at least for an instant. And then you start going down, and the velocity in the y direction increases at a rate of 9.8 meters per second every second. So these two are not the same like they were in the x direction. And then we have delta y equals v naught y t plus 1/2 a t squared. And again, a in the y is equal to negative 9.8 meters per second every second in the j hat direction. Sometimes I write it like this just to remind you what acceleration means. It's how much you change your velocity every second. You change your velocity by 9.8 meters per second every second in a downward direction. If you're going up, If you're coasting up, then obviously that acceleration is going to slow you down. Whenever the acceleration vector and the velocity vector are in opposite directions, you're slowing down. But on the way down, right, your velocity is down, your y component of the velocity is down, your acceleration is down, so you speed up. You're going faster and faster in a downward direction. And then v squared y equals v naught squared y plus 2ay delta y. Okay. So these are the things you need to know to solve just about all the projectile motion problems you're going to have. Of course, what is the same in both lists? Really, you only have one equation here in the x direction. And then you have all four of them in the y direction. I will tell you this, probably the ones you use the most are this one and this one. Sometimes you'll use this. Very rarely will you need to use this. But, you know, you can. But time is the link. Remember that when you have two-dimensional motion, that means that we're moving in the x direction while at the same time moving in the y direction. And there's, you know, so the time you see here will be the time you see over here. And actually, the biggest trick when you're solving projectile motion problems is to realize that, hey, I can, depending on what's given, maybe I use the x direction information to solve for time and then apply that in the y direction to solve for delta y or the final velocity in the y direction. Or vice versa, you can use this equation, you know, using the quadratic formula to solve for time, and then you plug it in here. And you've got it. So really, the overall strategy when you're solving these problems is to use the kinematic equations as we've been doing in the x direction separately from the y direction, linking them with time. Now there's also another thing that you should realize. If I have a projectile I'm launching, okay, so here's the initial velocity and I'm launching it from the horizontal direction, it will have some theta. This is called the launch angle. Very well named. It's just the angle at which you're launching it from the horizontal direction. And so we can say, well, v naught x, I think it's pretty easy to see that v naught x is just equal to v naught times the cosine of the launch angle, and that v naught y is equal to v naught sine of the launch angle. Okay. Now what I'm going to do, because I'm really running out of time, I'm just going to show you a few tricks of the trade, a few things that you can use to make solving these problems easier. And then it's just a matter of working a lot of problems and just practicing. Okay? So here's a type of problem that you'll see. I call it the kickoff problem. It's football season now, and so you know you go watch a football game on TV or in person or whatever, and they kick the ball off. And so the ball will start at the ground. It will launch with a certain angle, theta, and a certain initial velocity, and it will go up like this. And it will land, you know, unless somebody catches it, let's just assume that it just hits the ground. Now, remember, we can draw a motion diagram of this, by the way. Just look at it right here. Here, the velocity vector, remember that the velocity vector is always tangential to the trajectory. So see how the trajectory is flattened out? So my velocity, overall velocity vector is a little bit shallower angle now. And that makes sense, of course, because what happened to the y component of the velocity? It got smaller. But what happened to the x component of the velocity? stayed the same. Or at least I tried to draw it the same. So since the y velocity is shrinking as it reaches the top, this little triangle showing the x and y components of the velocity vector, this angle shrinks until when you're at the very top, of course, the only component of the velocity is like that. And then, of course, whoops, let me erase that. I need a better eraser, huh? So remember that the velocity vector is always tangential to the path, and so now we've got a y velocity is like this, but the x velocity stays constant. So this part, this, and ultimately just before it hits the ground. Now, here's one thing. When they say, what is the final velocity? They mean the velocity just before it hits the ground, okay? Because obviously if it hits the ground, it's not a projectile anymore in the sense that there is another acceleration acting on the ball. When it hits the ground, what's the acceleration on the ball? There's a big upward acceleration on the ball. There's a force of impact with the ground that's causing it to accelerate upwards, or decelerate if you want to think of it that way. But we're looking at the ball after it's left the foot of the kicker and just before it hits the ground. So we're looking at the ball while it's in free flight. Okay, there's no other interactions. It's only the interaction with Earth's gravity that we're looking at. We're ignoring air resistance. Okay, now here's a trick. If you have something very nice and symmetrical like this, here's one of the things I think you'll realize. When you get to the very top, you're halfway across. And, by the way, the time it takes to go up whoop, is exactly the same as the time to go down. So it's the same amount of time to go up as to come down. Unless we have a problem like this. And we launch it off the edge of the cliff. So let me, oh, this isn't fair if you're taking notes, sorry. Let me just redraw it. But now it's going to get here, but then what does it do? It just continues all the way down. And so now you have to, it's going to go farther, its horizontal range is going to be greater, I mean its delta x is going to be greater, its delta, now it has, by the way, when you're going from here to here, what is the delta y? It's 0. This is an important realization. If you get a problem, a kickoff problem where it hits the ground at the same height with which it was launched, you can assume this, the delta y is equal to 0, which is a big deal when you're trying to figure stuff out. If you say, oh, delta y is equal to 0, you can plug it in here and solve for time very easily. How much time did it take? And once you know the time, you can plug it in here to figure out delta x. So if it's a symmetric problem, you can figure out the time it takes to go here, here. By the way, the velocity x is equal to v naught x, but the velocity in y is equal to 0 at the very top of flight. That's something you can use when you're using these kinematic equations to solve these problems. Okay, so anyway, I think this gives you the basic stuff you need to solve all the kinematic equation problems. Now, if you look in the book, and let's see if I can find it here, there is some stuff that I'm running out of time, so I'm just going to want you to go over. They figure out the horizontal range and maximum height of projectile, okay, and they derive some equations. Like they have this, the height equation. What's the maximum height? It's right here. And then they figure out what's the maximum range. It's right here. The range is, just how far it goes. I don't really like these equations very much. I don't really use them. I always try to derive it using the kinematic equations. But they're there. They can save you some time when you're solving a problem. Just make sure you understand how they're derived. they're derived very nicely right here and here in the book. So I'm telling you, and this is a college level class, and professors do this all the time when they're running out of time, read the book. And if you have questions about horizontal range and maximum height of a projectile, we'll bring it up next time. So that is it for today. So long.